For an early motorist, pressing the brake did not necessarily produce the confident, immediate response a modern driver expects. The pedal might tighten a band around part of the drivetrain, or pull a network of rods and levers toward brakes, acting mainly on the rear wheels. The automobile would slow, but as road speed increased, the limitations of those arrangements became harder to ignore. A driver approaching a corner, a horse-drawn wagon, or an obstruction ahead could close the throttle and apply the brakes, yet the machine still carried the energy it had accumulated while accelerating. This created one of the defining contradictions of early automobile development. Engineers were rapidly learning how to build stronger engines. Improved roads encouraged higher speeds, and manufacturers competed to make cars travel farther and faster. Stopping technology had to follow, but the answer was not simply a larger pedal or a stronger pull on the existing mechanism. The difficulty reached into the architecture of the vehicle itself. Early automobiles did not share one braking design. Some systems acted on the transmission or driveshaft. Others used bands or shoes at the wheels. A hand lever might control one set of brakes while a foot pedal operated another. Many depended primarily on the rear axle. These arrangements were not irrational. At the modest speeds and weights of the first motor cars, simple mechanical brakes could provide useful control, and rods, cables, pivots, and levers were technologies manufacturers understood well. A brake was fundamentally a friction device. Press one surface against a moving member, convert motion into heat, and the vehicle slows. What changed rapidly was the amount of energy the friction system had to absorb. Kinetic energy rises with the square of speed. If the same car doubles its road speed, the energy that must ultimately be removed during a stop increases roughly fourfold. A brake adequate at 10 miles per hour, therefore, does not face merely twice the task at 20. The friction surfaces must absorb far more energy while still allowing the driver to maintain control. This relationship meant that an improvement in engine performance could expose a weakness in braking without any component having become worse than before. The automobile had simply moved beyond the conditions for which the older system was comfortable. Hard deceleration revealed another limitation. As a vehicle slows, the forces at its tire contact patches change. Because the center of gravity sits above the road, braking transfers load toward the front axle. The front tires carry more vertical force, while the rear tires become more lightly loaded. A rear-dominated braking system therefore asks the tires losing load to perform much of the stopping work while leaving substantial grip at the front unused. Apply enough force at the rear, and those tires may begin to skid before the front axle has contributed what it could. Early engineers did not describe every aspect of this behavior using modern terminology, but practical experience made the consequences increasingly clear. More of the available tire contact had to participate in slowing the car. Bringing brakes to the front wheels, however, raised another concern. Those wheels were also responsible for steering. Designers worried that a front wheel that locked on a slippery or uneven road might interfere with directional control. Such fears were not baseless. Roads could be muddy, rutted, loose, or greasy, and early front brake systems were not always coordinated with the rear axle. Some arrangements even left the driver operating front and rear brakes through separate controls. A poorly judged application could lock one axle while the other remained underused. Henri Perrot became an important figure in demonstrating that front-wheel braking could be engineered more effectively. Working with Argyll in Scotland, Perrot developed mechanical arrangements that allowed brakes to operate on the steering wheels while accommodating their movement. The 1912 Argyll 15 HP used his four-wheel braking system, and a United States patent followed in 1913. The achievement mattered because it attacked the first major weakness exposed by increasing performance. Instead of relying mainly on the rear axle, the automobile could use all four wheels to create braking force. Yet that improvement immediately made another problem more visible. If one pedal was to command four brakes, how should the effort be divided among them? Mechanical systems answered through physical linkages. A pedal could move a cross shaft, which pulled rods or cables, which passed through pivots and levers before reaching the individual brakes. Equalizing devices attempted to distribute force between the branches. Properly maintained, such arrangements could work extremely well. And four-wheel mechanical brakes remained successful for years. Their difficulty lay in coordination. Every joint introduced clearance and friction, wear accumulated. A rod adjusted slightly differently from its opposite number could cause one brake to apply earlier. Cable stretch altered travel. Chassis movement and axle motion had to be accommodated without upsetting the geometry. The problem was no longer merely where friction should be applied. It was how one command from the driver could reach four moving corners of the automobile in a predictable way. Hydraulics offered another path. The attraction was not that liquid somehow stopped the wheels. Brake shoes still pressed against drums, friction still converted motion into heat, and tires still provided the final connection with the road. What changed was how the driver's effort traveled from the pedal to those friction surfaces. A pedal could move a piston inside a cylinder. That piston pressurized to confine liquid, and the pressure could travel through pipes towards cylinders at the wheels. The principle was older than the automobile. Pressure applied to a confined, effectively incompressible fluid is transmitted throughout that fluid. For vehicle designers, this provided an elegant alternative to routing every braking command through a chain of rods and pivots. At the master cylinder, pedal movement created pressure. At the wheels, that pressure acted against pistons that moved the brake shoes. Cylinder dimensions could be selected to provide a useful force multiplication, allowing a relatively modest pedal input to create substantial force at the drums. Hydraulics did not guarantee perfect braking balance, nor did they remove the need for adjustment. Drum condition, shoe clearance, friction material, tire grip, and wheel cylinder dimensions still influenced the result. The advantage was architectural. Fluid pressure could be carried around the chassis through lines rather than depending solely on the geometry of long mechanical connections. Several engineers explored this possibility, which is why the history resists a simple single inventor story. Malcolm Loughead, who later changed the spelling of his surname to Loughead, developed important hydraulic automobile brake systems during the 1910s, including four-wheel designs using external contracting bands. Other experimentation occurred as well. Frederick Henry Royce has been associated with earlier hydraulic brake work, and reports from the period describe hydraulic applications on commercial vehicles. These efforts show that engineers in several places had recognized the usefulness of fluid pressure. The harder challenge was turning the principle into a reliable road car system. Hydraulic brakes demanded effective containment. Lines had to survive vibration. Connections could not leak. Pistons needed seals that retained fluid while allowing smooth movement. The liquid itself had to remain suitable across operating conditions. Air presented a particular problem. Unlike brake fluid, trapped air compresses. If it enters a hydraulic circuit, part of the pedal stroke can be consumed compressing the air instead of moving the wheel cylinder pistons, producing a soft response and reducing confidence in the system. In the 1910s, manufacturing cylinders, seals, fittings, and pipes with the reliability expected of a safety-critical system was a significant undertaking. Mechanical rods might loosen or require adjustment, but their behavior was familiar to manufacturers and mechanics. Hydraulics introduced different failure modes and demanded new service knowledge. A convincing design, therefore, had to survive roads, weather, repeated use, and imperfect maintenance rather than merely work in a laboratory. Frederick Duesenberg approached braking from a world in which performance was already central. He and his brother August built reputations through advanced engines and racing machinery. Competition rewarded speed, yet racing also exposed weak control systems quickly. A car capable of accelerating strongly needed brakes that could respond consistently when that speed had to be removed. Duesenberg filed patent applications in November 1920 covering hydraulic arrangements for controlling brakes at all four wheels from a common input. The production car that followed became the landmark. Introduced in 1921, the Duesenberg Model A used four-wheel hydraulic brakes with internal expanding shoes. It became the first production automobile recognized for employing four-wheel hydraulic braking. The sequence is important. Perrot had already demonstrated four-wheel mechanical braking. Loughead and others had explored hydraulic actuation. Duesenberg's significance lay in putting four-wheel hydraulic brakes into a production automobile. Inside the drums, hydraulic wheel cylinders moved the friction elements outward against the rotating surface. At the driver's end, a master piston generated the pressure. The pipes between them replaced much of the mechanical linkage that would otherwise have divided the pedal's motion across the chassis. The visible action remained familiar. The driver pressed a pedal. Beneath that simple movement, however, the method of communication had changed. A mechanical system transmitted displacement through rods, shafts, cables, and levers, whose geometry determined how the individual brakes responded. The Duesenberg system converted the driver's motion into hydraulic pressure and sent that pressure toward four wheel brakes. Its patents described using a single actuating member to command the system. That addressed the issue that had become increasingly important once four-wheel braking itself was accepted. How could several brakes be controlled without relying entirely on an elaborate physical network that had to remain carefully balanced? The use of internal expanding shoes was also significant. Loughead's earlier arrangements had included external bands contracting around drums. In the Duesenberg system, the friction mechanism operated within the drum, where wheel cylinders forced shoes outward against its inner surface. The design still required maintenance and careful manufacture, but it brought together several principles that would become common in passenger cars. The breakthrough arrived at a moment when braking demands were changing quickly. The early 1920s automobile was no longer confined to the performance of the pioneer era. Engines had become larger and more powerful. Racing accelerated technical development. Better roads allowed ordinary motorists to maintain speeds that earlier cars could reach only occasionally. A braking system now had to dissipate substantial energy repeatedly while maintaining useful stability. Four-wheel hydraulic actuation gave designers a practical way to control front and rear wheel brakes from one pedal without making every force depend on an increasingly complicated arrangement of rigid mechanical connections. It would be tempting to treat the Model A as the moment hydraulic brakes won and mechanical systems disappeared. The industry did nothing of the kind. Duesenberg produced advanced and expensive automobiles in relatively small numbers. Large manufacturers faced a different set of risks. Mechanical brakes were understood, and factories already possessed the tooling, suppliers, and service knowledge to produce them in enormous quantities. A hydraulic system required suitable seals, accurate cylinders, reliable fittings, appropriate fluid, and mechanics who knew how to fill and bleed the circuit correctly. Leakage raised concerns that did not look like a bent rod or broken cable. Air could compromise pedal feel. A manufacturer building hundreds of thousands of cars had to consider whether an innovation would remain dependable when serviced far from the factory by owners and garages of varying skill. This is why adoption rarely follows engineering superiority in a straight line. Cost, production investment, patent arrangements, customer confidence, maintenance practices, and corporate caution all matter. A design may be technically attractive, yet commercially inconvenient. Another may remain in service for years because the industry already understands how to build and repair it. Hydraulic braking needed proof beyond an expensive performance car. Chrysler provided one of the most important demonstrations in 1924. Walter P. Chrysler, working with engineers Fred Zetter, Owen Skelton, and Carl Breer, was developing a car intended to offer advanced engineering without occupying the exotic price territory of Duesenberg. The first Chrysler Six arrived with a high-compression six-cylinder engine and several technical features that distinguished it in the market. Among them were four-wheel hydraulic brakes fitted as standard equipment. That detail marked a different kind of milestone. Duesenberg had put the system into production 3 years earlier. Chrysler showed that four-wheel hydraulics could become a part of the standard specification of a more broadly positioned passenger car. Braking could now be presented to ordinary buyers as a reason to choose one automobile over another. Period advertising emphasized the advantages of Chrysler's four-wheel hydraulic system and its ability to apply braking effort in a coordinated manner. This shift in marketing revealed how much the automobile market had changed. Early publicity often celebrated the basic ability to complete a journey, climb steep gradients, or reach a remarkable speed. By the 1920s, manufacturers increasingly competed on refinement and control as well. The capacity to accelerate remained exciting, but customers were learning to evaluate how confidently a car slowed, steered, and responded to its controls. Chrysler's success did not cause every competitor to abandon mechanical brakes. Many companies continued refining rod and cable-operated systems. Improved equalizers and better geometry produced strong, dependable braking when properly adjusted. Ford's Model A, introduced later in the decade, became one of the best-known mass-produced cars to retain mechanically operated four-wheel brakes. Its existence is a useful reminder that the historical contest was not between a functioning hydraulic system and useless mechanical brakes. Both approaches could work. The question concerned the compromises manufacturers were willing to accept. As automobile suspensions became more sophisticated and wheels moved relative to the chassis, flexible hydraulic lines offered an increasingly convenient connection between body-mounted controls and wheel-mounted mechanisms. A mechanical linkage could accommodate the same movement, but doing so generally required more joints or cables and careful adjustment. Hydraulic lines could be routed around components and could follow steering or suspension motion without reproducing every change mechanically through a series of levers. These advantages became more valuable as vehicle architecture evolved. Even so, some manufacturers took more than a decade after the Duesenberg Model A to adopt four-wheel hydraulic brakes. That delay reflected caution as much as resistance. Brakes were too important for manufacturers to experiment casually. Seal materials had to improve. Cylinders had to become more consistent. Brake fluids needed predictable properties. Service shops had to learn how to identify leaks and remove air from a circuit. Once those problems became manageable, hydraulics stopped looking exotic and began to look practical. By then, the argument for front-wheel braking had largely been settled. During heavy deceleration, the additional load on the front tires allowed them to contribute a substantial portion of the stopping force. The engineering challenge moved toward proportioning that contribution rather than debating whether the front axle should brake at all. Excessive rear braking could cause the lightly loaded rear tires to lock and threaten stability. Front brakes therefore tended to do more work, especially as speeds and vehicle mass increased. Engineers used drum sizes, shoe geometry, wheel cylinder dimensions, friction materials, and later dedicated proportioning devices to shape the balance between axles. Hydraulic pressure provided a convenient medium through which those design decisions could act, but equal pressure did not mean identical braking force at every wheel. Real automobiles did not require perfectly equal forces, because the available grip was not equal under hard deceleration. This distinction is important. Hydraulic braking's value was not that fluid magically equalized every wheel regardless of conditions. Its advantage was that the control system became easier to configure and integrate around the behavior engineers wanted from the vehicle. Once this architecture was established, another limitation moved to the foreground: heat. brakes slow a car by converting kinetic energy into thermal energy. Drum brakes absorb that heat in their rotating drums and friction linings. One moderate stop may cause little difficulty, but repeated heavy applications or a long downhill descent can raise temperatures faster than the assembly can cool. As drums heat, they can expand. Friction materials can change behavior, and the brake may require greater pedal effort to produce the same deceleration. This brake fade reminded engineers that improving actuation did not remove the thermal problem at the wheel. It simply allowed the driver to command the available brakes more effectively. Larger drums, improved ventilation, better linings, and refinements in drum construction followed. These developments formed the next stage, rather than a rejection of hydraulics. The pressure circuit remained useful while the friction hardware evolved around it. Power assistance later altered the driver's experience again. Heavier and faster cars required substantial braking forces, yet manufacturers increasingly wanted pedals that did not demand exceptional leg strength. Vacuum servos and other boosting systems could add force before the master cylinder generated hydraulic pressure. The pedal became easier to operate even as the brakes became capable of stronger deceleration. What the driver felt was simplicity. Beneath the floor or firewall, the mechanism handling that input was growing more sophisticated. Reliability also improved through changes in hydraulic architecture. Early systems typically used a single circuit. A severe leak at one point could compromise pressure throughout the system. Later, dual circuit arrangements divided the brakes into separate hydraulic paths, so that one failure did not necessarily eliminate every service brake. Warning devices could alert drivers to pressure loss. Hoses, seals, reservoirs, and steel lines improved, and hydraulic braking became a platform on which additional safety could be built, rather than a novel feature requiring justification. Disc brakes provided another major development at the wheel. Instead of expanding shoes against the inside of a drum, a disc brake uses a caliper to squeeze friction pads against a rotating disc. Its open construction can release heat efficiently and offers good recovery after exposure to water. As discs spread, particularly on front axles where much of the braking work occurs, the wheel end mechanism changed significantly. The hydraulic principle remained. Pressure generated near the pedal still traveled toward pistons at the wheels, but those pistons now moved calipers rather than drum shoes. The continued usefulness of hydraulics became clearer precisely because the friction mechanism could change without abandoning the basic control architecture. Anti-lock braking extended that adaptability further. Earlier drivers had to judge how hard they could brake before a tire stopped rolling and began sliding. Once a wheel locks, steering authority and available friction can change abruptly. ABS introduced sensors that monitored wheel rotation and valves capable of reducing and restoring hydraulic pressure when a wheel approached lock. The pressure circuit that had once simplified the connection between one pedal and several brakes became something an electronic controller could manipulate many times per second. The driver still asked the car to slow with a single familiar motion, while the system beneath that action had gained the ability to respond differently at individual wheels. None of these later developments changed the final relationship between tire and road. A brake can generate enormous torque at the wheel, but it cannot create grip that the tire does not possess. Wet pavement, loose gravel, ice, worn tires, gradients, vehicle load, and driver reaction all affect the distance required to stop. Heat still has to be managed at the friction surfaces. The importance of hydraulic braking lies somewhere more specific. It gave automobile engineers a flexible and controllable way to carry the driver's input through an increasingly complex vehicle and apply braking at multiple wheels. This helps explain why mechanical braking should not be treated as a failed technology discarded once a superior invention appeared. Four-wheel mechanical systems represented genuine progress. Perrot's work helped show that the front wheels could participate effectively in braking. Mechanical equalizers and linkages gave manufacturers practical solutions at a time when hydraulic seals and service infrastructure were immature. Those systems remained viable because they met the requirements of many cars. Hydraulics gained ground as those requirements changed. Suspensions evolved, performance increased, passenger car refinement became more important, and manufacturers sought systems that could be integrated with new forms of assistance and control. In that environment, the ability to route pressure through lines rather than coordinate every wheel through mechanical geometry became increasingly attractive. The historical sequence, therefore, matters more than any single claim of invention. Perrot and Argyll demonstrated an important mechanical four-wheel system in 1912. Loughead and other experimenters pursued fluid-operated brakes during the following years. Duesenberg's Model A placed four-wheel hydraulic internal expanding brakes on a production automobile in 1921. Chrysler's Six brought the arrangement into a broader passenger car market in 1924 as standard equipment. Manufacturers that followed contributed refinements in materials, cylinders, balance, drums, service procedures, and reliability. The system matured because many separate problems were solved gradually. There was no moment when hydraulic pressure eliminated every weakness at once. Instead, it removed enough difficulty from the transmission of braking force that engineers could concentrate on the next limitations. This development also changed the driver's relationship with the brakes. On an early car, the control mechanism was often physically understandable. Pressing a pedal or pulling a lever visibly moved rods and tightened bands. Wear could show itself as increased free play, and adjustment was often a normal part of ownership. As hydraulics became established, the driver's visible action grew simpler while more of the work moved inside cylinders and lines. One pedal became the familiar interface to a system extending to all four corners of the car. The owner no longer needed to think about equalizer geometry during every drive. Mechanics still had to understand fluid condition, seals, shoe clearance, and bleeding, but routine operation increasingly depended on engineering rather than constant adjustment by the user. This change paralleled a wider transformation in automobiles. Early cars demanded significant mechanical awareness. Owners might adjust ignition timing, manage lubrication, repair tires, monitor cooling water, and learn the peculiarities of their transmission. Over time, manufacturers moved more of these responsibilities inside the machine. Braking followed the same direction. A system that once exposed its mechanical relationships to the driver gradually became a coordinated subsystem whose complexity remained largely hidden until maintenance was required. That transition mattered because automobiles were becoming ordinary transportation. A mass-market car could not assume every buyer was a trained mechanic. Controls had to behave consistently enough that attention could remain on the road. Hydraulic braking contributed to that shift without eliminating the need for driver judgment. Speed still affected stopping distance. Poor road conditions still demanded caution. A driver who entered a corner too fast could not depend on fluid pressure to change the laws governing tires and momentum. What improved was the reliability with which a reasonable pedal input could call upon the brakes available at the vehicle's wheels. By the middle decades of the 20th century, that expectation had become so normal that older arrangements seemed increasingly foreign. Drivers came to expect the foot brake to operate the primary brakes at all four wheels. Separate hand controls moved toward the role of parking or emergency systems, rather than being an ordinary supplement to the service brake. Pedal effort became more predictable. Front brakes took on much of the work during hard stops. Brake service still mattered, but the driver did not normally have to think about how force was divided through the chassis. The transformation is striking when compared with the pioneer era. A car that once relied on a drivetrain brake or rear wheel mechanism could evolve into a machine in which one hydraulic command reached four brakes, later assisted by boosters, protected by redundant circuits, and modulated electronically. The control visible to the driver remained almost absurdly simple compared with the engineering hidden behind it. That simplicity can make the history of braking less dramatic than stories about engines or racing records. Acceleration is theatrical. It produces noise, speed, and spectacle. Braking is successful when almost nothing dramatic happens. The car simply slows where the driver expects it to. Yet that uneventful response required decades of work because stopping a moving vehicle is a problem of energy, traction, heat, control, and reliability all at once. Early automobiles exposed those elements separately. Rear brakes showed the limits of using only part of the available tire grip. Four-wheel mechanical systems brought the front axle into the process, but increased the challenge of coordinating several brakes. Fluid pressure offered a new way to transmit the driver's command. Duesenberg demonstrated that approach in production. Chrysler helped show that it belonged in a passenger car intended for a broader market. Later engineers improved the friction hardware and layered assistance, redundancy, and electronic control onto the hydraulic foundation. The result was not that stopping became physically effortless in the literal sense. The vehicle still had to surrender the same kinetic energy. What became effortless was the driver's interaction with an increasingly sophisticated process. That distinction is why the history should not be reduced to a simple contest between bad mechanical brakes and good hydraulic ones. Mechanical braking was an essential stage in understanding how all four wheels could contribute. Hydraulic actuation became important because it suited the increasingly integrated automobile that followed. It allowed force to travel through a flexible network, adapted well to steering and suspension movement, and gave engineers a foundation that could accept later improvements without forcing the driver to manage them directly. In 1912, Perrot's four-wheel mechanical system showed that braking need not remain concentrated at the rear. 9 years later, Duesenberg placed hydraulic four-wheel brakes into production. Chrysler then helped push the concept toward mainstream passenger car acceptance. Across those milestones, the brake pedal itself did not undergo a dramatic, visible transformation. The machinery behind it did. That is the central thread running through the story. The earliest motorists could build speed before the automobile possessed an equally mature means of controlling it. Engineers first expanded braking to all four wheels, then found better ways to coordinate those brakes, and eventually built entire safety systems around the pressure created by one driver's foot. The automobile had learned how to build speed long before stopping became effortless. Hydraulic braking mattered because, at last, one pedal could control the force needed to bring that speed back down.